Hi guys. What we're going to be discussing in today's lesson is how to evaluate a logarithmic function and determine what its domain is going to be. Now, generally speaking, a basic logarithm with no transformations applied to it has a domain from 0 to positive infinity, where x cannot equal 0 because that's where the vertical asymptote of an untransformed logarithm lies. Well, here in the first statement, what it's telling you to do is that since the function, a logarithm function, has to have a domain of, positive numbers greater than 0, what it's telling you to do, it says to evaluate the function and see when is x greater than 0. Now to show you kind of what that looks like, we have a log of some kind, and we're going to have some kind of a function that we're evaluating the log with, log base b of something. Now, generally speaking, anything inside of the parentheses, we would, consider those horizontal transformations of some kind. But we can also look at whatever's in there as a function, because that's where a lot of times x is going to reside. But what it's telling you to do here is to say whatever the function in that parentheses is, set it greater than to 0, and then whatever x, or typically it's x, but whatever variable we have for our function, evaluate it, solve it for x, and that'll tell you whatever is left over. We'll say x is greater than that number, and that'll tell you what the domain of the function will be. Now, what we do here can vary depending on what is actually the function inside of those parentheses, whether it is a linear function, a quadratic function, or something else, some other kind of polynomial or whatever. That'll kind of tell us a little bit about what to do when we actually evaluate it. And we'll see some examples about that here in a second. Now, there's a second way that we can kind of evaluate a logarithm to determine what the function is. The second statement that you see here says, use the properties of the functions that we know to determine when the overall outputs are greater than 0. Oh no, let's go back. Oh, stop it. Greater than 0, there we go. Computer doesn't want to cooperate today. So, again, we have some function, right? Log base b, and we'll consider this some kind of a function here, whether it's a linear or whatever. So whatever that function is, we can look at the function by itself, the whatever's in the parentheses, we can look at that by itself and say, when will the function's outputs be positive, meaning whatever is in here. If we just look at that as a function by itself, disregarding the fact that it's working with a logarithm, if we look at that function by itself, we can also use that to help us determine what the domain of the logarithm will be. Because the domain of the logarithm has to have a domain of positive numbers greater than 0, then this step here is another way of looking at a logarithm and determining what the domain will be. So there are two kind of approaches that I'm going to show you how to do. The first one that we'll just kind of refer to as, I don't know, method 1 maybe. So we'll call this method number 1, and we'll call this method number 2. Well, in the first method, we'll kind of look at it from an algebra standpoint, where I literally just take a function, set it greater than 0, and solve for x. And the other method will be, well, how would we look at the function inside of the parentheses and use that to determine what the domain of the logarithm would be. So here's our first example. Function p is a logarithm with base 2, and so we say log base 2 of 2x plus 3. Now inside the parentheses, we can look at it one of two ways. The 2x plus 3 by itself, we can just think of those as, a transformation to the basic logarithm, where everything inside of the parentheses kind of behaves opposite of what you expect. So the whole number 2 that's in front of the x, that would actually be a horizontal compression by a factor of 2. And the plus 3 inside the parentheses says to take the basic function and shift it 3 spaces to the left. Well, what you see in the picture on the right is a table of values and a graph of the logarithm, showing you essentially what it should look like if you were to graph it, and from there you can get a good idea of what the domain should be. Well, method number 1 says to take whatever's inside of the parentheses, the 2x plus 3, make it greater than 0 because the domain of a logarithm has to be greater than 0, and then solve for x. So I'm going to move the 3 over and get 2x is greater than negative 3, and divide both sides by 2, and x will be greater than negative 3 over 2, or about 1.5. So the domain of the logarithm will be from negative 3 over 2 to a positive infinity. And that is essentially what the answer is that we're looking at. Now that's a really easy one to do because it's a logarithm. Or I'm sorry, because the stuff inside of the parentheses was just a linear function. And if you look at the picture on the right, you can kind of see at about where x is about negative 1.5, that's where the function stops using the x numbers. So the domain works. And looking at the table, you can see once I actually hit the number negative 1.5, we no longer have any x numbers at work. So the domain, yes, should be from negative 3.5 to positive infinity, where 3.5 is not included. Now, let me show you method number 2. Method number 2 is more of a graphical approach with whatever kind of function that we have. So the function inside the parentheses is 2x plus 3. Okay, if we were to graph the 2x plus 3, we would have a y-intercept at a positive 3, and we'd have a slope of positive 2. So I could count down 2 and to the right once to get a slope here. And so that's essentially what the graph would look like. Well, method number 2 is basically asking, okay, well, where is x when y stops being positive? Because the domain of the logarithm has to be numbers greater than 0, generally speaking. So that means everything that is below 0 on the y-axis, we wouldn't actually worry about in terms of how we're looking at this function to determine what the domain is. So all we really care about is where y is positive. And I want to know at what point on the x-axis do I stop becoming positive, because that tells me where the domain ends. So here, if I start here on the x-axis, which happens to be where x is equal to negative 3 over 2, I can use from negative 3 over 2 to the right forever. I can use all of those numbers because that is where y will produce positive numbers if I substitute it into the linear function. So that's another way of showing that for the logarithm, the domain will be from negative 3 over 2 to a positive infinity. Now, the graphical approach for this one is actually a little bit more complicated than the algebraic approach, even though a linear function is about the easiest thing to graph. But, excuse me, I want to keep doing both methods because at some points there are going to be functions that aren't quite as simple as a linear function, and it'll actually be, I think, very helpful to see it as a graph in addition to any algebraic approach that we do. So let's take a look at our next example. Here we have a function with natural log where the base is e, and in the parentheses we have 4 minus x squared. Now again, those by itself would occur just some horizontal transformations of the graph, but this is what we're trying to do is evaluate it for the domain. So what x numbers actually work? Now again, in the picture that you see here, it's kind of giving you a table of values and a picture of the graph of the logarithm. And you can see that we only have so many x numbers that we're using. There's a very small amount. So from here, this looks like about -2, and this here looks about a +2. So we want to know, how do we determine that domain? So algebraically, again, we're going to just take the expression that's inside of the parentheses, 4 minus x squared, and I'm going to say that that has to be greater than 0. And just like in the previous example, we'll solve for x, so I'll move the 4 over, and I'll get a negative x squared is greater than -4, divide by -1 to make the variable positive, and by dividing by -1 with an inequality, we have to turn the symbol around. And so x squared is going to be less than 4, and if you take the square root of both sides, you'll get x is less than a positive and a -2. Now this is where, algebraically, some of us might start to get a little confused. It's like, okay, well, how can x be less than a +2 and less than a -2 and produce the graph that you see in the picture? This is where I think the graph is really going to be helpful because it will allow us to demonstrate what I need to do algebraically from this point on. So we're going to come back to the algebra approach here in a second, but let's look at the function in the parentheses, the quadratic function in parentheses, as a graph by itself. So negative x squared and a 4 says that I'm going to touch the y-axis at a +4, and we've already essentially solved the quadratic, saying that it would have roots at a +2 and a -2. So when we graph this, it would go like so. And again, we want to ask ourselves, where are the y numbers positive? Okay. Well, the y numbers are positive. The y numbers are positive between -2 and +2 on the x-axis. So because the y values of the quadratic are only positive between -2 and +2 on the y-axis, that essentially is letting me know that the domain of my logarithm is going to be between -2 and +2. Okay, so how does that tell me for sure what the algebra approach is going to do? Okay, so let's look at a number line. So number line, here's 0, here's 2, here's -2. We know that the domain, algebraically, is going to have something to do with the -2 and the +2, but algebraically by itself, we don't know, unless we do the graph, we don't know just with what we did in red, if the domain is going to be in between the +2 and the -2, or if it's going to be everything but what is in between the +2 and the -2. Okay, so here's what we're going to do algebraically at this point. If we see our domain is going to be a range of some numbers like we see here, something maybe in between +2 or -2, or everything but what's in between +2 and -2, I'm going to substitute 0 into that function, and just into the x minus, or the 4 minus x squared part. And if the answer is positive, If the answer is positive, I'm going to only use the numbers between positive and negative 2. Conversely, if the answer was a negative number, we would use anything but the numbers that would be between positive and negative 2. So again, let me just put that here. So if you want to put it in your notes, if the answer is negative, use everything except numbers between positive and negative 2. So I'm kind of running out of room here, but let's kind of look right here. If I say 4 minus 0 squared, well, that just simplifies to be a positive 4. So because I get a positive answer when I substitute a 0 into the expression that's contained in the parentheses, that tells me that the domain has to be the numbers that we algebraically determined between positive and negative 2. The domain must be contained within those two numbers. So again, I would write the domain as an interval notation between positive and negative 2. And if we had gotten a negative number, if I had put a 0 in there and gotten a negative answer, we would have said that the domain would have been everything except the numbers contained between positive and negative 2. But substituting that 0 thing really doesn't make sense unless you kind of look at the graphical approach of the function contained within the parentheses. Looking at the function in the parentheses, we can clearly see that we're only looking at the positive numbers on the y-axis will be between the negative 2 and the positive 2 on the x-axis. So that's why if I substitute a 0 into the expression of the logarithm and I get a positive answer, that's what tells me use the numbers between what we found. And if I get a negative number, that tells me use the numbers that are not between the numbers that we found, the positive 2 and the negative 2 in this case. So here, let's take a look at our next to last example. There's only going to be 4. But here, algebraically speaking, we have the natural log of, and you could think of like this in parentheses. What we would look at here, the radicand, the way that we would determine the domain of what we have for the logarithm is I'm only going to take the radicand, the 5 minus the 3x, and I'm going to set that greater than 0. And this one algebraically is going to be a pretty straightforward one. So solve for x, move the 5 onto the other side, and I'm going to get negative 3x is greater than negative 5. Divide everything by negative 3, and when I divide with a negative number, the inequality symbol turns around. So negative 5 divided by negative 3 gives me a positive 5/3. So the domain of the logarithm should be everything that's less than 5/3. So I'm going to say from negative infinity up to, but not including 5/3. Okay, so let me look at the graphical approach just to kind of confirm what we would do here. Again, the graph is simply going to take the function that the logarithm is being evaluated with. In this case, we have a radical function. Well, if we were to solve the radical function here and try and determine where would it be, well, when we work it out, the root, the one root that the radical function has, happens to be at positive 5/3, which is about 1 2/3. So about 1 2/3 is right around here. The y-intercept of that would be about 2.2. So 1, 2, 3. So 2.2 would kind of put me about right here. So the radical function kind of goes like that. And again, all we would ask is, where are the y numbers positive? Well, the y numbers are positive from every point along the x-axis, from here everywhere to the left here. So that's, again, how I can say that the domain of the logarithm would be from negative infinity to positive 5/3. And again, the picture that's been provided for you here on the right is a picture of what the logarithm is when we graph it. And at about or at about positive 5/3, which is the 1.667 number, that's where the domain breaks down because we have to be bigger than that number. So every negative number past that, or every number to the left of that number on the x-axis, will work for the domain. So the last one here, and this is another one where seeing the graph of the function contained in the parentheses is actually, I think, going to be pretty helpful. So this one, the function in the parentheses of the logarithm is a rational function, meaning that if we set that greater than 0, then we're going to have some function where I'm going to have x minus 2 that would give me a root at x is equal to a positive 2, and the x plus the 3 that would give me a vertical asymptote at x is equal to negative 3. So on a number line, I don't know why my pen doesn't want to give me straight lines very well today. So let's say this is 0. So this is positive 2, and this is negative 3. So again, we're kind of going to be looking at a range of numbers between, either the domain is going to be contained between the negative 3 and the positive 2, or the domain is going to be everything but the numbers between negative 3 and positive 2. So what we're going to do, again, kind of referring to the quadratic one that we used as an example earlier, this also is going to produce a domain that has a particular range. So if I substitute, not substitute, if I substitute 0 into the rational expression in the parentheses, if we get a positive number, then the domain will be between the negative 3 and the positive 2. And if we get a negative number, then the domain will be anything but between negative 3 and positive 2. So it would be from negative infinity up to the positive 2, not included, and from the 2 to a positive infinity. So let's do that. Let's say 0 minus 2 over 0 plus 3. Well, that simplifies to be negative 2/3. So because we get a because we get a negative number when we substitute a 0 into that expression, then this tells me that's what the domain of this particular logarithm should be. And that's kind of what you're seeing in the picture being provided for you. When I graph the logarithm, we use every number to the left of the negative 3 and every number to the right of the positive 2 and nothing in between. Now let me just go one more time to the second method, the graphical approach. If we graphed the rational function, I'm going to have a root at a positive 2, a horizontal asymptote at a positive 1 because it's balanced and x over x simplifies to be 1, and I'm going to have a vertical asymptote at the negative 3. And the y-intercept happens to be that negative 2/3 that we figured out, so negative 1, negative 2/3 is kind of right there. So if I were to graph this, it would go oh, I missed my root, like that, and like that. And again, we want to ask ourselves, where is y positive? Between what x numbers? Well, y is positive between the negative, it's negative, y is negative. I have negative answers between the -3 and the +2. So everything that's in between the -3 and the +2 on the rational function that we graphed here, this is where y is negative. So that tells me that the domain of the logarithm has to be everything else but what's contained between those two numbers, because that is where I get a negative number on the rational function. So again, the domain will be from -infinity to -3, including 2 to +infinity. Oops, and I made a mistake on my domain up here. I just realized it. This should be -3, not 2. So either way that we would do it, with the algebraic approach or the graphical approach, we can, when we have something that says, well, the domain's going to be between a set of numbers, or it's not going to be between a set of numbers, we kind of say, we can say, okay, well, if I substitute a 0 into whatever we have here, and I get a positive answer, then the domain is going to be in between the two numbers, like we saw with the quadratic expression in the second example. Or if we get a negative number, then the domain is going to be everything that's except for what's in between those two numbers. Well, that's kind of what we're seeing with this expression. And the way that we were able to determine that by substituting 0 is really looking at the graph of the function that's simply contained within the parentheses and saying, well, between what x values is y going to be positive? And that will also allow us to determine the domain of the function. So some of them will be a little bit easier to do than others. Like you saw with the linear one and the radical one, those are pretty straightforward. But with the quadratic one, and like with this one, the rational, not quite as straightforward. So we have to employ a little bit of prior knowledge on functions with our logarithms, and that will allow us to really understand how we determine the domain of a function. So if you have any questions, again, as you've been taking your notes, I hope you've been writing them down and bring them to me in class. Otherwise, I look forward to seeing you, and thanks for watching. Have a good one.